So folks, in our first example, we computed the chain rule, but we did so in a very naive fashion, and what we did was we basically did substitutions and then relied on our Calc 1 knowledge of taking derivatives and coupled that with our new knowledge of partial derivatives. So what I'd like to add is that the above method often works, but it is not what I want you to do in this section. And here are some reasons for that. The above method would work only if we're given each function explicitly. And sometimes we want to be able to work with a non-explicitly given function and still talk about its derivative using a chain rule. And even if we are explicitly given the function, sometimes this might be overly tedious to calculate. You might have found it a little bit difficult to keep track of all of the different components as we were doing that derivative. So what we do is we seek another method. We want a multivariable chain rule. And that's what we're going to teach in this section. The multivariable chain rule can't really be stated generally. Instead, we explain it on a function by function case, and we do so by building what we call a tree diagram. So this is the most important skill for this section here, is building these tree diagrams. So what I'd like to do is let's repeat this initial example where we've got this function up above here. Z is a function of x and y, and x is a function of u and v, and y is a function of u and v. And let's go ahead and show the multivariable chain rule this way. So what we're going to do here is we're going to put our dependent variable up above here, and then we have these variables here, x and y. In a moment I will call those intermediate variables. And then we said, well, x was a function of u and it was a function of v, as was y a function of u and a function of v. Okay. Folks, really quickly, this is how I choose to draw my tree diagrams. Different books draw tree diagrams differently, so you might see a tree diagram drawn like this, x and y, and then down here we'd have u and v, and they might be drawn in more of a pyramid fashion. I find these diagrams a little bit cluttering and sometimes too difficult to draw if we have a whole lot of interaction. So I will draw our tree diagrams this way. So the way you interpret this tree diagram then is to say that x depends on the variables u and v, and z depends on the variable x and y depends on the variables u and v. So we'll label this in just a minute, but for right now let's just go with the structure of this. Okay. So what we're going to do when we go to give the multivariate chain rule, partial z, partial v, as we were asked to do, we're going to look at this tree and we're going to trace all of the routes that get us from z down to that independent variable v. So there's one route that can get me there. Another route that can get me there is this way right here. Oops, wrong way. Is this path right here. Okay. So because rates are additive, and we're not really going to give a proof for this chain rule, but because rates are additive, we can simply add the rate of change taking this route and the rate of change taking this second route together to give us the total rate of change as we vary the independent variable v. So here's how we're going to construct this. We're going to say that partial z, partial v is equal to partial z, partial x, where that's running that leg of that branch, and then partial x, partial v. Partial x, partial v. So what we have here is this tree is sort of a mnemonic way for remembering how to compute the chain rule. And I'm using the paths to help me set it up, and so each leg of the path gets multiplied to the other legs of the path. By the way, you're not allowed to do this mathematically, but a nice symbolic way of showing that you've computed a portion of the derivative of z with respect to v is to, which you're not allowed to do, imagine these expressions as if they were fractions. And notice then, in that case, you could cancel out those two factors, and you would be left with partial z, partial v. But that is not something we're allowed to do mathematically. It just gives us a confirmation that we've set up the path correctly. But that was only taking the blue path to the independent variable v. We could also take this orange path to the independent variable v. So we would add to that partial z, partial y times partial y, partial v. Again, you could imagine canceling out those two factors, and you've got partial z, partial v. And what we've done is we've additively summed together these two different ways we could obtain a rate of change, and rates are additive. So what we've got now is sort of we've built ourselves a recipe for computing partial z, partial v. To do so, we need to compute all of these intermediate partial derivatives. Well, just using our skills from the previous section, we know that partial z, partial x, if we go back to the original function here, if we take partial z, partial x, we're going to treat the cosine y factor as if it were a constant, and we would just have the derivative of x squared, so that would be 2x cosine y. Okay. We're also going to need partial x, partial v. So if I go to compute partial x, partial v, what we would have, so x is a function of u and v, but if I treat u as a constant and take the rate of change in the v direction, we would have 3v squared. We also need these partial derivatives. So if we compute partial z, partial y, going back and looking up that original function, we would have minus x squared times the sine of y. And if we compute partial y, partial v, if we go back up and we look at what y is as an expression of u and v, if we take the partial derivative of y with respect to v, we get minus 14 u to the 5th, v to the 6th, taking that derivative. So some people might say, well, this seems like a lot more work. You had to draw a tree diagram, then you have to compute all these individual pieces. But the nice thing is notice we haven't had to worry about anything like the product rule as we set everything up. And so this is a lot easier method for keeping track of all of the components mentally, and sort of less taxing than this method up here. As a reminder, folks, I want you using this method that we're teaching here to do these problems. So now we're ready. We can go ahead and actually just give this expression, partial z, partial v, and that would be equal to 2x cosine y times 3v squared plus negative x squared sine of y times minus 14 u to the 5th, v to the 6th. What I can now do, folks, is since I want this to be I want to think of z as a function of v, is I could replace the x's and y's that I have here with their explicit descriptions up above here. So let's go ahead and do that. So I went ahead, folks, and I took this answer that we had, and everywhere I saw an x, let's put that in a different color, everywhere I saw an x, I replaced it with the rule for x, and everywhere I saw y, I replaced it with the rule for y. I also did some simplifying of some minus signs, but here you can see I've now given the chain rule derivative for the partial derivative of z with respect to the variable v. And you can come take a look up here. That should be identical to the answer that we got above. Sometimes there may need to be some manipulation of those expressions to see that they're equal. But in this case, it's pretty straightforward to see that this expression up here is equal to this expression down here. And we have indeed computed that partial derivative, in this case, using the tree diagram method for computing the multivariable chain rule. And this is how we're going to compute our multivariable chain rules from here on out.